Hello everyone. Thanks to everyone for watching this video. My name is Qi Dao. I'm an architect and engineer. Today's video is titled Viscous Flow, and it is going to provide you a broad overview of the viscosity and also the Navier-Stokes equations. I'm going to give you an overview of what I'm covering in today's video. First at all, we will have a look at some fundamentals of the viscosity, then move on to the mathematical derivations for the Navier-Stokes equations, then wrap up with conclusions. Everyone has an intuitive understanding of what the viscosity of a fluid is. Honey is more viscous than oil, and oil is more viscous than water. Viscous fluids feel thicker and don't allow as easily. But because it is such a fundamental parameter that defines how fluids behave, it is worth developing a more in-depth understanding of viscosity. To do this, let's start by looking at fluid flowing over a flat surface. It's sometimes useful to think of fluid as flowing in layers, with each layer moving at a different velocity. When two layers are moving relative to one another, because they are flowing at different velocities, a shear stress develops between them. This is similar to how a frictional force develops between two solid objects sliding relative to one another. The effect of this shear stress is most obvious in flow close to a wall. The wall imparts a large shear stress onto the fluid particles that are in contact with it, causing them to have zero velocity. This is called the no-slip condition. The larger shear stress is transmitted through to adjacent layers of flow, slowing down flow close to the wall and resulting in a velocity profile that looks like this. The magnitude of the shear stress acting between the layers of the fluid is closely linked to the slope of the velocity profile, du over dy, where u is the fluid velocity and y is the distance from the wall. The slope is more in the free stream. The fluid layers are moving at almost exactly the same velocity, and so the shear stress will also be very small. But close to the wall, the velocity changes very suddenly. In this region, the slope is large, and so the shear stress is also large. For most fluids, the relationship between the shear stress and the slope of the velocity profile is linear. And the constant of proportionality is what we call fluid viscosity. In engineering, it's usually denoted using the Greek letter mu. We can think of viscosity as the internal friction of a fluid in motion. It has the effect of smoothing out differences in velocity by increasing the shear stresses in proportion with the velocity gradient. We can express the linear relationship using this equation. This is called Newton's law of viscosity, and fluids that obey it are said to be Newtonian. It describes how easily a fluid will flow. The viscosity mu is sometimes called dynamic viscosity, as this differentiates it from the kinematic viscosity, which is the dynamic viscosity divided by the fluid density. Let's look at how a small fluid element like this one will deform as it flows. If du over dy is positive, the upper surface will move faster than the lower surface, and so over a time period delta t, the upper surface will travel further by a distance equal to delta u times delta t. This generates a shear strain that we can calculate using trigonometry and the small angle approximation. By rearranging, we can see that the slope of the velocity profile is equivalent to the rate at which the shear strain is applied. This makes sense if we consider how solids and fluids respond to applied shear forces. Solids respond to a constantly applied shear force with a finite amount of deformation, whereas fluids respond by deforming continuously. They flow for as long as the shear force is applied. So now we can write Newton's law of viscosity in a different form, like this. This looks a lot like Hooke's law for shear that we see in solids, except instead of being a function of the strain, the shear stress is a function of the rate at which the strain is applied. Next, we will introduce the differential analysis of the viscous flow. In general, two types of forces need to be considered: surface forces, which act on the surface of the differential element, and body forces, which are distributed throughout the element. For your purpose, the only body force, delta Fb, of interest is the weight of the element, which can be expressed as this equation, where g is the vector representation of the acceleration of gravity, in component form shows here. Surface forces act on the element as a result of its interaction with its surroundings. At any arbitrary location within a fluid mass, the force acting on a small area delta A that lies in an arbitrary surface can be represented by delta Fs as is shown in this figure. In general, delta Fs will be inclined with respect to the surface. The force delta Fs can be resolved into three components: delta Fn, delta F1, and delta F2, where delta Fn is normal to the area, delta A, and delta F1 and delta F2 are parallel to the area and orthogonal to each other. The normal stress, sigma n, and the shearing stresses are defined as these equations. On the plane ABCD of the right-hand side figure, which is parallel to the YZ plane, the normal stress is denoted as sigma xx, and the shearing stresses are denoted as tau xy and tau xz. We now can express the surface forces acting on a small cubical element of fluid in terms of the stresses acting on the faces of the elements, as shown in this figure. It is expected that, in general, the stresses will vary from point to point within the flow field. Thus, through the use of Taylor series expansions, we will express the stresses on the various faces in terms of the corresponding stresses at the center of the element of this figure, and their gradients in the coordinate directions. For simplicity, only the forces in the x direction are shown. Note that the stresses must be multiplied by the area on which they act on, obtain the force. Summing all these forces in the x, y, and z direction, use these equations. The resultant surface force can now be expressed as this equation, and this force combined with the body force, delta Fb, use the resultant force, delta F, acting on the differential mass, delta M. That is, delta F equal to delta Fs plus delta Fb. The expressions for the body and the surface forces can now be used in conjunction with the previous equation to develop the equations of motion. In component form, we can obtain these equations, where delta M equal to rho times delta x, delta y, delta z, and the acceleration components are given by these equations. It now follows that these equations, where the element volume delta x, delta y, delta z cancels out. These equations are the general differential equations of motion for a fluid. Since these equations include both stresses and velocities, there are more unknowns than equations, and therefore it is necessary to establish a relationship between the stresses and velocities. For incompressible Newtonian fluids, it is known that the stresses are linearly related to the rates of deformation and can be expressed in Cartesian coordinates as these equations, where P is the pressure, the negative of the average of the three normal stresses, that is, as indicated by the figure in the Morgan. The stresses can be substituted into the differential equations of motion and simplified by using the continuity equation for incompressible flow as shown here. For rectangular coordinates, see the figure in the Morgan. The results are expressed here. We have rearranged the equations so that the acceleration terms on the left side and the force terms on the right. These equations are commonly called the Navier-Stokes equations. A principal difficulty in solving the Navier-Stokes equations is a result of their nonlinearity arising from the convective acceleration terms. There are no general analytical schemes for solving nonlinear partial differential equations, and each problem must be considered individually. For most practical flow problems, fluid particles do have accelerated motion as they move from one location to another in the flow field. Thus, the convective acceleration vanishes because of the nature of the geometry of the flow system. In these cases, exact solutions are often possible. The Navier-Stokes equations apply to both laminar and turbulent flow, but for turbulent flow, each velocity component fluctuates randomly with respect to time, and this added complication makes an analytical solution intractable. Thus, the exact solutions referred to are for laminar flows in which the velocity is independent of time, steady flow, in a well-defined manner. Now we will try to use the Navier-Stokes equations to the steady laminar flow. We consider flow between the two horizontal infinite parallel plates of figure A. For this geometry, the fluid particles move in the x direction parallel to the plates, and there is no velocity in the y or z direction. We have these boundaries. In this case, it follows from the continuity equation. We have this boundary. Furthermore, there would be no variation of u in the z direction for infinite plates. And for steady flow, we have this boundary. If these conditions are used in the Navier-Stokes equations, they reduce to these equations, where we have set gx equal to 0, gy equal to minus g, and gz equal to 0. That is, the y-axis points up. We see that for this particular problem, the Navier-Stokes equations reduce to some rather simple equations. From these equations, we can derive these equations to obtain these two expressions. Note that for this simple flow, the pressure gradient, differentiate x from p, is treated as constant as far as the integration is concerned. Since the p equation is not a function of y, the two constants c1 and c2 must be determined from the boundary conditions. For example, if the two plates are fixed, then u equal to 0 for y equal to plus or minus h, because of the no-slip condition for viscous fluids. To satisfy this condition, we obtain c1 and c2. Thus, the velocity distribution becomes this expression. This equation shows that the velocity profile between the two fixed plates is parabolic, as illustrated in figure B. The volume rate of flow Q passing between the plates for a unit width in the z direction is obtained from the relationship as this equation. The pressure gradient, the differentiate x from p, is negative, since the pressure decreases in the direction of flow. If we let delta p represent the pressure drop between 2 points a distance L apart, then we have these equations. The flow is proportional to the pressure gradient, inversely proportional to the viscosity, and strongly dependent on the gap width. In terms of the mean velocity, v, where v equal to q over 2h, the q equation becomes this expression. The q and v equations provide convenient relationships for relating the pressure drop along a parallel plate channel and the rate of flow or mean velocity. The maximum velocity, Umax, occurs midway, y equal to 0, between the two plates, as shown in figure B, so that we obtain the Umax expression. The details of the steady laminar flow between infinite parallel plates are completely predicted by this equation to the Navier-Stokes equations. For example, if the pressure gradient, viscosity, and plate spacing are specified, then we can determine the velocity profile, the corresponding flow rate, and mean velocity. In addition, since the pressure gradient in the x direction is constant, from the p equation, we can obtain the F1x expression, where PO is a reference pressure at x equal to y equal to 0, and the pressure variation throughout the fluid can be obtained from the new p equation. For a given fluid and reference pressure, PO, the pressure at any point can be predicted. From conclusions, what we learned. The viscosity of a fluid is a measure of its resistance to deformation at a given rate. It can be conceptually as quantifying the internal frictional force that arises between adjacent layers of fluid that are in relative motion. Basic differential equations describing incompressible viscous flow, the Navier-Stokes equations, are introduced. Some simple solutions for steady, viscous, laminar flow between parallel plates are included. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I'm happy to answer any questions. Thanks for your watching.